Here we have a cope elimination reaction. Here's the general overview and what MCPBA is, because that's how you get the OH group at the end, right over here. So diving into the mechanism, there's like 4 R groups, like with like carbon or like any halide or anything you want. And so this arrow attacks the N, which is a partial nitrogen R group, which is a partial positive charge, and then the O group acts as a nucleophile and attacks at H, leading for that bond with the H on the original product to go there, forming this alkene, and like plus the products of this OH and like N double R thing, the nitrogen and the 2 R groups right here. So it follows the Hoffman rule. So like the steric influence is really great and like an outcome of the elimination, meaning like it creates 2+ alkene products. So if you have a regular like alkene or like reactant right here, there's 3 alkenes formed and the percentage of them, and if you add the other methyl group onto it, there's only 2. So this one is preferred right here because the H matches up with the CH, so there's less energy going into that. But this one is less preferred because it's a CH3 matching up with the CH2 and stuff like that. Or not stuff like that, that's just how it is. Yeah. Next, here's like the transition states of it, like with a 5-membered cyclic transition state and like their sterical demands, stuff like that. Also, I measured the bond energy of them. So since it's an aromatic ring right here and has double bond, and like a couple more carbon bonds, it's like 8 carbon bonds and 1 double carbon bond. So each totals to like 3,390 kilojoules per mole. So right here, the stereochemistry matters. Where here we have it behind and then like in front. And like it was 0% chance like this will happen, and this is 100% chance like this one will happen, because it makes more sense like stereochemically, because if it's in front, it's not gonna like automatically turn to the back right there, and it's gonna stay like that, and it's easier to form double bond on this carbon, and like same rules apply here. And here's a more detailed mechanism of the example with like a pentene or like a pentane, or yeah, right here with all that, if you'd like to see. It'd take too long to explain what's going on, so I'm going to move on. And here's an example in recent literature, which is a synthesis of a 3,4 disubstituted isoxoxylase via an anandamine in brackets 3+2, like a cycloaddition. So here it is right there. It's following it like another alkene is formed right here, because that was not here previously, and it's like that part's eliminated and it's right here. So next, like there's 2 additional questions. So like, how might you speed up the elimination reaction? Cope eliminations are considered E2 eliminations, so a few factors affect this rate. So it increases if the strength of the strength of the base increases. So if it's a strong base like an OH, NOH, KOH, it'll do it faster than a NH3 or like ammonia or CH5, C5H5N one. And the solvent, if the solvent is aprotic, polar, or both, the rate of the reaction increases immensely. So some polar aprotic solvents would be like acetone and DMF. So that would be the preferred one. Same like as if the leaving group is also as strong. So the better the leaving group, the faster the reaction will be. So iodide is the largest, so it will be the best leaving group, and it just goes down the line of halide. It also occur faster if it's on the more substituted halide. Here you can see here. And like how would I predict delta G and K for this reaction to be? We know for E2 reactions that as temperature increases, so does the yield of products. So that means heat is favored and produces more products and breaks more bonds. Since heat is favored and it increases activity, that means entropy increases, further meaning is exergonic. It also depends on the amount of bonds broken. Generally, around 2 bonds are broken in a cope elimination, so G is less than 0 and K is greater than 1.